Good afternoon, everyone. I'm Ella, and it's my absolute pleasure to welcome you all on behalf of eMobility Plus and First View Group to today's insightful webinar on modeling electric motors and drivetrains. First and foremost, we would like to extend our sincere gratitude to our partner, COMSOL, for their continued support in making this session possible. Before we begin, I'm delighted to introduce our distinguished expert speaker for today's session. Dr. Avinash Nelson, Technology Specialist at COMSOL. Dr. Nelson is a seasoned engineering professional with deep expertise in electrical machines, low frequency electromagnetics, and FEM simulation. He earned his PhD from NIT Calicut, where he conducted advanced research on nanocomposite materials for electrical machine winding insulation. He also holds an MTech in Power Systems from VNIT Nagpur. With a strong background in both academia and industry, Dr. Nelson has previously served as an assistant professor and brings valuable insight into areas such as generators, motors, dielectrics, electrical insulation materials, and drives. So today's session will explore how electric vehicles are reshaping the automotive landscape, driving demand for innovative motor and drivetrain design. As engineers push the envelope of performance and efficiency, it becomes critical to understand the interplay between electromagnetics, thermal effects, structural integrity, and fluid dynamics. Through this webinar, we'll discover how COMSOL Multiphysics empowers engineers to simulate these complex interactions using the AC-DC module and battery design module, offering a comprehensive multiphysics approach to optimizing electric motors and drivetrains. You'll also witness live demonstrations and technical walkthroughs that show you how to harness simulation tools effectively in real-world EV applications. After the presentation, we'll host an interactive Q&A session where Dr. Nelson will address your questions. So feel free to submit them anytime during the session via the Q&A box on your screen. Before we dive into the technical presentation, we'd like to play a short video that showcases how COMSOL is driving innovation across the automotive sector. I now request my team to kindly play the video.
Developing designs and performing experiments virtually is both cost and time efficient. With COMSOL Multiphysics simulation software, you can be sure your results accurately represent the real world. By studying multiple physical effects on one model, no matter the order in which you combine different physics, the software handles them together and solves the mathematical and numerical model equations and provides you with the model results. The entire simulation process takes place in the same software environment. You only need to learn one workflow, no matter the physics involved or the nature of your experiments. Depending on the scenario, you may want to model single physics, one-way multiphysics, or fully coupled multiphysics. The COMSOL software offers all three, and the true advantage of COMSOL Multiphysics is the ability to model unlimited multiphysics, where all physics in a model interact, affect each other, and together influence the model results. If you need to add any physics, including your own equations, to your model, you can. The application builder in COMSOL Multiphysics gives you the tools to build your own simulation apps. The Startup Wizard and drag and drop functionality help you quickly turn your models into simulation apps with customized user interfaces, restricted inputs and outputs, report generators, and more. This way, you can spread the advantages of simulation to colleagues and customers by compiling your apps as standalone executables via COMSOL compiler, or by making them accessible by web browser via COMSOL server. Understand, predict, innovate, and optimize your processes and designs with COMSOL Multiphysics.
Thank you, team, for playing that video. So now, moving ahead, without further ado, I'm pleased to hand over the session to our expert, Dr. Nelson. The floor is yours, sir.
Thank you, Ala. I think the screen is visible to you. Yeah.
Yes.
Okay. So thank you for the introduction and very good afternoon to you all. Today's our webinar is on modeling electric motors and drivetrains with COMSOL Multiphysics. So you all had an introduction to the COMSOL through the video as well as whatever been spoken about the webinar from Ala. So if at all you look around you, you can see that let us say the world is driven by electric motors, starting from the ceiling fan above you, as well as maybe the motor inside your printer, or in any domestic appliances we have, or in the heavy industrial drives. Mostly at every place, we are dealing with electric motors, and we need to control this motor in a particular way. So if at all you see the overall power generated in terms of the electrical power generator, most of that power is utilized in satisfying the electric drive loads that vary in all or in different places. So whenever we have the electric drive, it will have three parts. Sorry, I got muted. Yeah, now I think it is fine. So when we are dealing with the electric motors, we have to control how a motor is going to be driven or what are the speed or characteristics. So for that, we need a power electronic converter before the motor, and we need the power source as well to drive the motor. So when you look at a drive or the whole electric drive mechanism, then we have three components there. One is the motor, another one is the power electronic converter that now we have, and the other one is the power source. In case of a ceiling fan, you have the regulators that we used to see in the older buildings or in the olden days is used to be quite bulky, using a resistive kind of control in terms of when it comes to the power control part. So that was happening up to some time. Then we got the power electronic converters. Now, if you see the ceiling fan regulator, it has become so robust and small with lesser losses, reducing the size of that particular regulator. All this is happening in front of our eyes, similar to the EV area that mentioned before. In electric vehicle part, we were not even thinking about having or replacing the IC engines with our electric motor let us say in the last 2 decades. But now we are actively thinking about it, and let us say we can even start talking about recharging the battery in a tea break or in a tea break as a near future thing to happen. So that way, in different sectors, both in the electric motor in terms of design, or it can be about, let us say, on the power electronic converter section or in the batteries, all these places are going through new changes compared to the conventional motor drives we have. So when it comes to that aspect, that is where we can say the numerical simulations are going to play an important role, and mainly in the prototype modeling, or as well as in, let us say, in optimizing the design of a motor, or it can be related to the electrothermal aspect of a power module or even battery. All this aspect, rather than making the prototype and testing it, why don't we first make it in simulations as a simulation scenario and see the realistic results and then go for prototyping. Then we are talking a lot about efficient utilization of our resources, and that is where COMSOL Multiphysics pitches in particularly in the aspects of modeling the electric motors, as well as I said, in the similar areas. So we are going to look into those all aspects, like how COMSOL is going to be beneficial in modeling electric motor, as well as in the other areas like power electronics, as well as in the battery module area, how it is going to be useful. So that with the same software, you will be able to do different physics or different aspects of the whole electric drive mechanism. So let us try to understand it more. So if at all you see the electric motor, you are all aware, here you are seeing an electric motor, and you are all aware that an electric motor principle is like you have a current carrying conductor placed in a magnetic field. Then yeah, so when we consider the motor, we place a conductor inside a magnetic field and it will experience the force. So that much is getting solved based on Maxwell's equations, and we can solve it in COMSOL multiphysics, which is based on an FEM. It is basically an FEM simulation software where the Maxwell's equations are getting solved. Whether it is stationary steady or the transient steady or frequency domain steady, we are resolving or we are solving the same Maxwell's equation with respect to particular application. So that aspect, if you take in terms of, let us say, how much of the electromagnetic torque is generated inside the motor, that much is for that much we are solving Maxwell's equations, and that is what is meant by single physics scenario. So in COMSOL multiphysics, we can deal with single physics scenario, as I explained already, like only solving the Maxwell's equations. Maybe in other physics like heat transfer, if you have the temperature difference between two plates, you can understand what will be the temperature distribution between those plates by solving the heat transfer principles or the heat transfer physics. That is another physics we have. In COMSOL, the major aspect is that we can solve single physics as well as multiphysics. So what is meant by multiphysics? As you are seeing in this figure, you have the current conductors going to the stator core, and that will generate some, there you will have the three-phase currents, and it will generate some amount of heat as the losses. So once that heat is coming out from this conductors, it will there will be heat transfer phenomena as well involved here, so that we can simulate simultaneously with the electromagnetic phenomena. Because in most of the realistic scenarios, it is very important. Once your coil is getting heated up, how the conductivity of the copper is going to vary with respect to temperature will matter. Maybe you have a synchronous generator, as we have in super thermal power generating stations. There, how much is the current flowing through the conductor, through the rotor conductors, which is making which is used for making the magnetic field, that will be very heavy. So the heat produced by will be very heavy, leading to changes in the material properties. So once that needs to be simulated in a simultaneous manner, like in every time step, what is going to be the effect of temperature on the current or current on the temperature, that we can do in multiphysics. This is not the only aspect. We can include what will be the vibration caused by the rotor by involving the fundamentals or the fundamentals behind structural mechanics. So all these things done together in a simultaneous manner is what is called as multiphysics, as the name implicates with COMSOL. So COMSOL multiphysics software can either do, we can either simulate the same thing using the single physics aspect, or we can do it multiphysics without having any boundaries or any restrictions on how many number of physics you can solve at a time. It is getting solved simultaneously. So that is the major aspect with COMSOL. So we will be getting into more details on how to model electric motors, and as well as on the what we can do with COMSOL in the power modules as well as in battery technology. But before that, I would really like to know the kind of participants we have, so that we can make the presentation in the similar way. Like whether you are currently a regular user of simulation tools, or are you like evaluating the simulation tools for any ongoing project, and based on some personal interest you are attending it, or you are really new to the multiphysics simulation. I hope you are seeing a poll question on your window and you can answer it. We will get back in like 1 minute. Okay, yeah. So yeah, I think that is enough time. May I continue, Ella?
Yes, sir. Yes, sir. Okay. Please.
Yeah. Okay. So some of you are regular users of COMSOL, but mostly are quite new to multiphysics aspect. So I think I will go on with having a generic introduction to COMSOL in terms of like how motor modeling can be done. But we will go into specific aspects provided in the time frame we have here. Okay. So 1 second. Yeah. Okay. Yeah. So first we will see the electric motor modeling part. Then we will slowly get into the power electronic module and battery technology. So those are the main objectives of this webinar, I would say. How we can model an electric motor, how we can utilize the capabilities of COMSOL for power modules, as well as for the battery technology. So in terms of an electric motor, if you observe, 1 second. Observe here, you can see a permanent magnet motor modeled in COMSOL. As you can see in this particular part here, these are the coils that will be wound, or that will be wound on the stator bus, which is shown as an extruded version here for better visibility. So we can model, we will be modeling the coils in COMSOL through either it can be modeled like as a CAD geometry of coils. That is a general aspect, but mostly in motor cases, we can once we define the geometry and of this coil or the motor, we can define these coils as multi-turn coils with a particular conductivity, as well as how much is the insulation thickness involved, so that we will be able to give the stacking factor of this particular coils. And these are placed in the stator slots as you are seeing here, which will be made of laminated cores. Both this portion of the stator slots, as well as the inside some of the inside part will be made of the laminated cores. And in terms of laminated cores, how much is the losses happening in the laminated cores, we can visualize, or we can use the empirical formula available, which is used mostly in industry, like Steinmetz formula or the Verotti equation, for defining the losses in the laminated core when we are going through the workflow. Apart from that, these are the magnet involved, which are placed here, like a number of permanent magnets on this rotor. That is why it is becoming a permanent magnet motor, and it is a 3D version of this one. If you see the entire software workflow, software GUI here, you can see a graphical window as shown here, where we will be making the geometry, as well as we will be seeing the results as well. Then we can see a model builder part here as well. In this model builder, it is done in a systematic manner. Like we will first define, or global definitions, you can see, we will define our problem very clearly. Then we will get into creating the geometry as the one you are seeing here through particular or a set of operations we have under geometry. Then we will be adding the particular physics. So in this case, as Ahla already mentioned, we are using AC/DC module, and inside in AC/DC module, since it involves the magnetic field calculations or implementation, we will be using the magnetic field part here. And in COMSOL, we have a particular set of modules for modeling the motor itself under magnetic field and mechanics. So using that, we will apply certain boundary conditions. As I already said, what is the number of turns of the coil, and what kind of phases you have. Here you can see the phases or the coils here, which will be corresponding to different phases. You can either design a 3-phase motor or an N-phase motor, like a 5-phase motor. But all are possible by defining clearly what is the excitation given to this motor, as well as from the number of poles, the number of slots and all. So once it is given, we will be ready to simulate it using FEM. And the next step will be meshing the whole geometry for FEM, and then we will conduct a particular steady step. So the whole process of electric machine modeling is done in COMSOL in this approach. First, we create geometry, then we go through applying the boundary conditions needed for FEM, and then we mesh it, and afterwards study. All of these things are systematically done in this manner here, making it a user-friendly environment to use. And that is the thing. And for different materials, we are having an elaborate material library in terms of AC/DC module or other built-in modules. So using the material properties, we will be assigning under the section of materials, and different material models can be implemented. Like you are dealing with the a complex permeability of the material, then we can include that as in the magnet part. Or we have a BS curve which involves the Giles Anderson kind of hysteresis loop. Then we can create our own BS curve, or view the hysteresis loop in a similar manner in terms of coefficients. So that this is the overall feasibility, I would say, or how we will be doing electric machine modeling with the AC/DC module. Now, once this electric machine modeling is done, then we can have other multiphysics aspect as well. But before getting into that, what all kinds of motors we can deal with in COMSOL multiphysics? There is no restriction as such. As I said, it is only about solving the Maxwell's equations in space, in respect to space and time, or in the frequency domain. So we can simulate the radial flex machines, which are the conventional machines that we have. As you can see in this particular machine, we have the rotor with a V connected the rotor core kind of a structure here, and we can either we can go for a 2D model. If you take this particular motor example, in the cylinder in this particular radial direction, you can have it use it as a 2D approximated model. If you are not considering the skewing of the rotor as well as the stator or the end rings, which does not matter much when it comes to the initial design. But if you want to consider a particular aspect like the skewing of the rotor involved, then you can we have a particular aspect called 2.5D modeling, which will help us do that as well. Then, or once we have a simulation, like whenever you are modeling a new motor or studying the characteristics of an existing one, normally first we want to see how the design needs to be done in the initial study part. That you can maybe go with 2D or 2.5D modeling. But once it is about validating the entire motor before prototyping, we can jump into 3D modeling, which will take some computational effort, but ultimately give you the proper results. So this is the way normally it works with COMSOL. Now, apart from radial flex machines, the axial flex machines and linear machines are gaining importance these days because of the high torque to weight ratio of the axial flex machine. Again, if you linear motor is also similar, which gets into the translational motion, which mainly involves either levitation or in some cryo applications where we are involving similar motions like the piston kind of motions are involved. Then linear motors are involved. So in COMSOL, we can model both the radial flex machines, axial flex machines, or the linear motors as well. So this is possible both in 2D, 2.5D, as well as in 3D. So this is what the capabilities we have, which are already inbuilt in COMSOL in terms of the electrical machines. Now, once we have the electrical machine running, or we made the rotating magnetic field based on the kind of excitation we give. Now, this excitation needs to be given so that we are having the proper speed torque characteristics, or we need to control the speed torque or power involved in the overall motor operation. That is where our power electronics converters will come into action. And in terms of power electronic converters, COMSOL can deal with in several layers. Like the first portion where the way COMSOL is going to deal with it is using the semiconductor module we have. If at all, let us say you want to see what is happening at the semiconductor junctions when it is involving a MOSFET or the newer gated MOSFET kind of, or the MOSFET kind of technologies we have, or a transistor, any kind of device we have in the micro level, we can incorporate a COMSOL to define the semiconductor properties, or how it is going to behave when we have a particular equipment in terms of or a semiconductor switch we have. That is one aspect. Another aspect is that you are seeing a power module here, and in this power module, once current is flowing and we have bus bars all along, then because of the current, you will have juice heating, and that is why heat will be generated. We can use the multiphysics aspect of COMSOL in order to evaluate where we are going to have hotspots generated due to temperature, and what is the effect of current density on that. Again, in a simultaneous manner, as I said, in multiphysics aspect. So this is such an example used in industry with power electronics. So we can model both this kind of the semiconductor level of aspect, as well as the overall power module simulation in multiphysics way using COMSOL multiphysics. Another strategy here we adopt is that in COMSOL we have an electric circuit module, which is part of the AC/DC module, where we will be able to connect the particular excitations as well as the lumped model of resistor, inductor, and capacitor, and some of the active switches we have, like whether it's a BJT or a MOSFET. All those things as a lumped model are available, which can be directly connected to the FEM model, making a co-simulation approach. in terms of the electric circuit, which is an analytical model, and coupled with the finite element method, is a numerical model, I would say. So this also is possible in terms of the power electronics approach. Now, in the battery modeling, that is quite new here, and we can again go from micro level to macro level, as in the similar manner I already said, whether it is from the in terms of chemistry, or we have the battery pack models, or it's about thermal management, or in conducting different kind of studies like cycle voltammetry, or the electrochemical impedance spectroscopy kind of analysis. That also is possible. We'll get back to that later. So this is the three parts of the drivetrains. Now we will get deeply into how electric motor model can be useful when it comes to multi-physics couplings. So as you are seeing in this figure, once we are using electromagnetic field physics in AC/DC, we will be solving the Maxwell's equation to get the electromagnetic field and develop the rotating magnetic field, calculate the Lorentz force, or the electromagnetic torque involved. We can connect it with electric circuit, let us say an inverter, through switches, which will be the part of the model where we can control the current excitations into a device through switches, or we can give our own analytical waveforms into the system so that it will replicate the same phenomena. That is what is done with the AC/DC module. Now, apart from that, it can be connected to the heat transfer. As I said, once the current goes through the conductors, it will generate heat, and that will we have the whole heat transfer phenomena related to that. And in some motors, it will be actively cooled, or it will be like passively cooled, or there will be heat transfer mechanism, natural convection will be involved. So that can be simulated with the CFT module available in COMSOL, again in the multi-physics coupled manner. As I said, whenever your current is flowing and your temperature is varying, the material properties will change, mainly on the resistivity as well as on the run-and flux density of the core material. Those can be simultaneously coupled in COMSOL multiphysics to see you the realistic results. Another major aspect, since it's an electromechanical conversion device, our motto is that we can simulate how the electromagnetic torque is going to interact with the overall structure. Like the rotor is having a mass and moment of inertia. There are bearings. The friction will involve. So how it can act on this, that can be dealt with the solid mechanics interface available in COMSOL. These are all separate modules available in COMSOL, but already are having particular multi-physics couplings available in COMSOL. Like whether we want to simulate the magnetostriction or the electromagnetic forces, we got magnetomechanics module as well as the nonlinear magnetostriction multi-physics interface to couple that. That is this. And again, through to heat transfer, maybe there can be thermal expansion. So there will be a coupling. We can couple heat transfer with solid mechanics in that way. And once you have vibrations, you will have the noise level on the outer domain, which we can couple with the acoustic domain, creating the vibroacoustic studies on the electric motor. This way, whether it is the thermal expansion or the vibroacoustic analysis or the torsional oscillation, all these things can be done in one single GUI using COMSOL multiphysics. Now, the major portion here is about optimization, because when you are designing a new module, we start with a particular design and we will have some objectives in mind so that we want to optimize our design. That we have a particular optimization module available, which will be where we can do multi-physics kind of optimization approaches, which we will discuss later. So I hope you got an idea on how the electric motor modeling aspects can be done, both as a single physics scenario or as a multi-physics scenario. So now, before getting into more details, let us try to understand where do you stand or what you really are looking for in terms of the electric motor modeling. Whether you are using for, let us say, the thermal analysis or the electromagnetic EM losses and all, or you are looking into noise and vibration studies in motor, or is it only about the motor design optimization? Or if you have any specific queries, then we can look at it now or later based on your answers on the poll.
So we can move ahead. We have received the answers from the audience for the poll.
Okay. Okay. So yeah, we will get along with the electric motor modeling part first. And once I go through the electric motor modeling, we will see a live demo, and then we will move on to the other aspects like the power electronic module aspect as well as the battery module part. So yeah, we will cover, like, I think you are interested both in the thermal aspect as well as in noise and vibration and as well as optimization. So we will cover as much as possible in this time duration. So first, if we look into the modeling of motors and mainly in the multi-physics aspect, the electromagnetics part we already have seen. Now let us say we are coupling it with the heat transfer. The major input to the heat transfer is the copper and iron losses happening in the motor. If you have the copper conductors in the stator as well as in the rotor, what is the amount, depending on the current going through the conductor, we will have the copper losses. So those losses will be directly coupled to the heat transfer module available in COMSOL. This particular machine is a synchronous motor drive, or there is a synchronous motor part. Along with that, using the electric circuit module available, it is becoming a complete electric drive. Like it is getting connected to the outside circuit, and you have a synchronous motor here, as shown in this figure. So now, when it comes to the material properties, some of the properties will depend on some of the property parts will depend on temperature. So we have to couple that as well. And whenever we are simulating this particular electric motor, either we can simulate it in stationary mode, or in the transient mode, or in the frequency domain mode. Now, as you are aware, once you apply the AC to the conductors, and your rotor will start moving slowly and it will come to a steady state. So it's a transient phenomena. But after a while, once it comes to a steady state, the same is going to happen again and again. So if this law, in terms of loss calculation, well, in mainly the laminated core part, we have Steinmetz model as well as Barotti model, where it is frequency dependent. So in order to, if at all we are conducting a transient steady, which is the case with motor, then we have to get the an understanding on how the losses are dependent with respect to frequency or with respect to harmonics. For that, a specific capability is the called as time to frequency losses, where we will be converting all the losses in terms of frequency from the transient data, considering the harmonics part as well. So this is how it is done in COMSOL by taking the losses and giving into the heat transfer module. In terms of both iron loss as well as in copper loss. In terms of copper loss, we already, since we are solving Maxwell's equation, it is able to accommodate both the skin effect as well as the proximity effect throughout the conductors. So that defines our losses. Now, once we have losses, as I said, the conductivity as well as the remnant flux density of the material, conductivity of the copper conductor, they can be defined, or they are a bit loosely coupled with the temperature. And using the temperature coefficient of resistivity or resistivity, we can define how the conductivity of the material is going to vary with respect to temperature, as shown in this model here. Like, either we can define as temperature independent, or in a particular simulation, when we understand that in the temperature range that we are dealing with, the conductivity is varying, then we have an option to include the variation of conductivity with respect to temperature. The same applies in terms of the remnant flux density as well. So this is the way we will be coupling the electromagnetics with the heat transfer module. Now, that is one aspect. And the another aspect is the major aspects is that how we can couple this to the structural mechanics. Using single physics, we will be able to understand how much is going to be the electromagnetic torque. But once you want to see how the bearings are going to have an effect on the overall mechanism or vibration, or how the misalignment of the rotor with respect to the stator is going to play a role, or the frame is going to play a role in the torsional vibrations, we will be coupling it with the mechanics module, or the solid mechanics module. There it can be done in two ways. One is called the magnetic elastic interaction, where we are trying to understand what is the deformation caused due to the specific effect of stresses. That is one way. Another way is the magnetic rigid body interaction, where we will be mostly looking for how much is the displacement of the rotor with the particular mass and moment of inertia when you have an electromagnetic torque. So these are the ways we can couple electromagnetics with the available mechanics module we have in the circuit. So in COMSOL. So once you have the mechanics module incorporated or coupled with our ACDC module, then we can study vibration as the one you are seeing here. This vibration is caused due to the rotor misalignment, and in the first figure you are seeing how the vibrations are happening, or the stresses are developed on the frame of this motor. In the second, you are seeing along with the rotor how it is going to play a role. Now, sorry. Yeah, in the third figure, you are seeing these are the two bearings we have on two sides. They're depending on the misalignment, how the bearings are going into vary its position, or the orbit of the bearings is what you are seeing this way. This way, we can study how the vibrations will be developed by coupling it through the mechanics using magnetomechanics, and we will be able to analyze different aspects of the vibration analysis in this way. Now, so these are the two major multiphysics couplings we have. One is heat transfer, another one is the magnetomechanics. Now, how it is really used in industry is what I would like to showcase. Now, you are all aware about the Volkswagen, which is a major manufacturer of EVs we have today. And this is a laminated core section, you can say. They are trying to see or optimize the strength of the rotor laminations, but it is a multi-physics kind of optimization approach. Like, we should not compromise both on the mechanical strength of the lamination. At the same time, there should not be a compromise on the magnetic flux density as well. Or maybe in the laminate, how much is going to the losses, all those terms are considered, and the research team conducted a deeper study onto that using COMSOL Multiphysics, and they ended up with a proper design for the laminated thickness. Now, once they got the design, the second using the research team, the next thing they did is making an application. As already you might have noted down in the video, once we create a real design, then we can have an application where we will be only varying some particular parameter, or we have a new electric motor design, what should be the new lamination thickness. For that, we need not do the whole simulation, but in turn, we can have an application where a particular parameter will be varied, and in terms of that, what should be the optimized design. They have developed it, and they are actively using it for making the electric motor laminations, or the design process. So as I said, application is playing a major role in terms of the efficient utilization of time. Like, even if a person is not knowing much about the whole aspect of COMSOL multiphysics or the physics, but once he get an application, he can just enter a parameter value and use it. That is one way of making it effectively. Another thing with electromagnetics, as I already said, in motor we have a transient phenomena, but if you take smaller sections of the transient phenomena, we can see that the rotating magnetic field is periodic. So once you develop a rotating magnetic field and you are in the steady state a steady state region, then you need not do it for every time step. Because once one revolution of the rotating magnetic field is going to repeat in every cycle for a particular operating condition. So that we can utilize by solving it in the time periodic approach available in COMSOL. So in the time periodic approach, it is not only like we will be solving it in a stationary kind of a study, but it is if at all we are incorporating the heat transfer along with that, then we will be coupling whatever be the losses happening in one cycle in a cumulative manner to the heat transfer module, so that we will see what is going to be the effect of the losses over a time in the motor. So this way, there is no compromise on the multiphysics approach, but if effectively we are able to save so much of computational time. Because when it comes to industrial application, we are trying one aspect of the analysis is to look into what is going to be the torque speed characteristics of a motor, or what will be the efficiency map, or what is the dependence of temperature with respect to efficiency. All these things are mostly done in steady state conditions. So that can be modeled quite easily and in a faster manner using the time periodic electromagnetics approach. And as I said, there is no change with respect to the multiphysics aspect. So in a traditional time-dependent analysis, what we normally do is that we will apply the excitation, then it will take some time, let us say some number of cycles to reach into the steady state, and every time step is getting repeatedly calculated, and that goes on. That is only needed in the transient phenomena, but in the steady state condition or in the time periodic analysis, what we are doing is that we will solve it for let us say one rotational cycle, and then we can accumulate that for different multiphysics approaches in the other ways. What you are seeing here is a permanent magnet motor, again utilizing a particular capability of COMSOL using the symmetry approach. like we are not modeling the whole motor in 2D, but the half of that is modeled because it is going to be time periodic with respect to this particular symmetry case. And what you are seeing here is that this is at a 1200 RPM speed and at current is 30. If you come from this one to this one, here the speed is same, but current is changed, and this corresponds to the electromagnetic losses happening in the all around the motor. And you can see that at a lower current, you are having lower losses in the material. At a higher current, you are having the higher losses in the material. And it majorly happens in the stator whenever your speed is low. Once your speed is becoming faster and faster, then you can see that the losses are also propagating to the rotor as well, because the conducting magnets will have losses involved when your rotational speed is increasing. But and again, the current is 30 from here to here, but when the current is lower, the losses are reducing, as you can see here. The same effect, since this is the electromagnetic losses happening, which will depend on what will be the temperature distribution all around. The same thing in terms of temperature distribution you can see on the other side, as you are seeing here on this side. And this corresponds to the efficiency map. Like, these are different operating conditions in terms of the speed as well as for the current, which will again get on with the torque as well. How much is the torque produced at different current values and the speed values. So with respect, we are having a torque speed characteristics here, and the other component we are trying to understanding is the efficiency. This is called the efficiency map of this particular motor, and we can see that the efficiency, how the efficiency is varying with respect to the speed as well as the torque in this manner, giving you the overall understanding on how your motor is going to behave under different speed torque conditions. So this particular example I explained to this extent because we are going to deal with it in the live demo tomorrow. Now, apart from the normal heat transfer aspect, we can also can model the magnetomechanics, as I said. Even though we are having a time periodic analysis, but we can have the eigenfrequency analysis of the vibrations involved or the noise involved in the similar manner. Now, once we have this kind of couplings, the major aspect when we design a new motor or in the industrial applications on design, and that is where optimization plays a main role. If at all, let us say we are trying to optimize only the stresses involved, then it will be a single physics optimization. So I can solve in this way. Yes, this is an optimization problem where we are changing the topology of the overall system. And in the first one, we are only optimizing the stresses involved in the motor, and this is using the AC/DC module. This one is using the solid mechanics module. We will have different optimizers cells, so we can which is not realistic. So when we are optimizing it as a multi-objective optimization problem, we are looking for optimizing in terms of the solid mechanics aspect as well as in the electromagnetic aspect, giving us a particular design which will be able to satisfy both the things. So that is the advantage we have the optimization strategy even with the time periodic analysis as well in COMSOL, that we can use optimization but in a multi-physics in way. Now, other aspects in optimization, particularly, it is not only applicable to AC/DC or motors, it is applicable to every electromagnetic or other physics field as well. We can do parameter optimization, where normally we will be changing some particular parameter like the coil radius or a particular thickness as a parameter and then vary it. That is one aspect of optimization. Another one is the shape optimization that we will see. And the third one is the topology optimization, like how, let us say, the materials, if they are varied in the way they are made, how it is going to have an impact on this overall thing. This is an axial motor, and it is about how to reduce the overall iron thickness of this one. This is an example of topology optimization. Now, as I said, in terms of parameter optimization, you can see in the figure, this particular conducting paths we have, how a small variation in the geometry can have an effect on the overall, both the mechanical aspect as well as the electrical aspect. That in that way, we will be just optimizing a very small or a particular parameter in the geometry, and then we will go for changing that parameter so that we have our optimized solution on with a particular objective. So that is with the parameter optimization. When it comes to the shape optimization, as you are aware, when we have the development of electromagnetic torque in the air gap, and the torque ripples will depend on the shape of the rotor surface as well. So how we can reduce the shape of this the ripples in the torque is done with the rotor surface optimization. We can implement different constraints while doing this optimization, like how much it can bend and all, what all kinds of shape changes are possible in an elaborate manner using the shape optimization module available in COMSOL. This is one way of dealing with it. These are the capabilities we have with COMSOL. Now, to better understanding how it is really done with COMSOL, we will be looking into the live demo involving the permanent magnet motor example, which is quite an easy one. At the same time, it tells you both the electromagnetic aspect as well as how we can couple it with heat transfer as well. And just before I showed you uh, showed you this graphs or this analysis on heat transfer and efficiency maps. So that is what we are going to deal with now in the live demo. Okay, yeah. So Ahlad, just let me know if I am sharing the screen correctly.
Yes.
One second. One second. Yeah, I hope it is visible, right?
Yes, visible now.
Yeah, I want to minimize this. 1 second. Or I will keep it on the other side. Okay, yeah, thank you. Yeah, so this is the permanent magnet motor model. As you can see, this is how the COMSOL multiphysics window will look like. 1 second. This is how the permanent magnet COMSOL window will look like. On top, whenever you want to make a new model, we will get into this way, and we will get into model wizard. As I said, we can model it in 3D, 2D, axisymmetric, or 2D, or all this kind of space dimensions are possible. In this case, we are going with the 2D physics. Now, once we come into the 2D physics aspect, we have different physics approaches, as I said, like AC/DC, acoustics, or heat transfer. All the modules are available. So inside AC/DC, again, depending on the kind of physics you are dealing with, we have different kinds of specific modules as well. So in this case, you are dealing with electromagnetic fields. So we can either go with magnetic fields, or we have another particular module called electromagnetics and mechanics. And we will be once you get into electromagnetic and mechanics, we can see three aspects of it. One is the rotating machinery magnetic, another one is the rotating machinery magnetic structure interaction. As I said, both interactions are possible: magnetic, elastic, magnetic, rigid body, and all. So if you are dealing with transient or a general study, we can go with rotational machinery magnetic. But this is a new one we have, which is called the rotation magnetic, but time periodic, which is going to save us much more time. Then I will add this physics like this, and we will get on to designing the whole. Designing the whole setup in the similar way. That is how this is made. Now, in the process of solving this problem, as I said, it's a permanent magnet kind of a motor that we are dealing with. First, we will be defining our problem very clearly, and that is where the global definitions comes in. So inside the global definition parameters, I can represent what are the number of poles, what are the number of slots, or the whole design data that we have in an industry or in a research environment. Maybe we will have a data sheet or an Excel sheet or a text file containing all this data: the number of poles, number of slots, the length, what will be the initial angle, or what is the rotational velocity of the rotor, or what is the electrical frequency, the current value, number of turns in particular coil. All these things will be known, and it might be available either in hand or as a document. So either you can input all this data as done here, or you can go and just load it from a file. It can be a text format or or an Excel sheet, but you can load it here in this parameter section. This is an important aspect because this is where you are really defining your problem in terms of all the design parameters. Now, once it is defined, we can create the geometry. Either we can, in the geometry toolbar, if you see, either using the available primitive shapes like circle, rectangle, or different primitives are there, and there are Boolean operations and transforms which will allow us to manipulate the primitive geometry so that you can achieve any kind of geometry needed. And whenever it is about making a chamfer or a fillet, or we want to avoid a particular section, which is section and all, we can have all this kind of specific aspect available in the geometry. So this is one way of doing that. Another way is that which is quite user friendly in terms of the electric motor design. If at all we consider any electric motor, mostly it will have a particular number of stator slots, and it will either it can be open or a semi-open or a semi-closed kind of a thing. Similar applies to the rotor as well. Maybe it is a permanent magnet rotor, or it's a induction motor, or the other way around. All these are quite standard shapes, and that is why we have something called the part library. In part library, if you check under ACDC, either it can be about solving different kind of coils. That is another section, both 2D and 3D. But in this case, we can get into the rotating machinery. As I said, both 2D and 3D versions are available. So in rotor, if you see, either it can be this kind of an embedded magnet, because when it's embedded kind of magnet, it is having a effect on the air gap electromagnetic torque ripples, and also now sometimes we prefer the embedded magnets as well. Or it can be as the particular V-shaped internal rotor as well, or a surface mounted permanent magnet rotor as well. In this case, we are using the surface mounted permanent magnet rotor. Once we incorporate that, the whole geometry is completely parametric. Like what should be the overall number of poles, or what will be the distance of the pole, or how much should be the fillet size happening here. All these things are directly accessible to manipulate. So once we include that, add the geometry, it will be implemented in the geometry. Same thing applies to the stator as well. Like we have normally one option we have is a slotted stator. Again, what kind of slots we have can be manipulated in the template available. So this way, we have already taken one internal rotor surface mounted, as you are seeing it here, as well as the external stator, as you are seeing in this one. So that is the slot and the rotor. Okay, 1 second. Yeah. So this alone is creating the rotor, and if you see instead of keeping the template in the template, I manipulated in this way. This is the number of poles. So I kept already in the parameters, it is defined as the number of poles is 10. Then I can directly go here and use that number of poles. And as you have seen here we are not modeling the entire motor and to avoid the computational time. Instead, I am using the using like how many number of poles needed to be seen, or the symmetry aspect. So it is done in this way. Okay, so this is the aspect that we are we are utilizing, the symmetry aspect, so that we need not simulate the overall geometry. Similarly, the slots also, if you see, there are different various options in slots, as you can see here. Like the overall number of slots is ns, but the number of model slots, it is depending on the symmetry. Like we are only defining half of the number of slots, and all the other parameters are defined here. Now, particular one aspect I would like to mention is the slot winding type. If you see the slot winding type here, it is given as 2, and depending on the kind of slots you are going to use, or you are going to use, we can define values here. Like if there is no partition, it will be type 1. If there is a radial partition, it will be 2. As you can see, there is a radial partition between the two between the winding. That is why it is given as 2. So this way, we are able to use the templates effectively in modeling the standard motor geometry. Or, as I said, we can go with the making a geometry our own using particular design. When it comes to an axial motor or a linear motor, maybe we are not having a particular template. That is one aspect. Another aspect is the CAD geometry. In some in industrial cases, we mostly have the CAD geometry available with us. We can use the import option available here to import the CAD geometry and work with that. So that is how we make the geometry in COMSOL. And once the whole geometry is assigned, mainly since it involves in a motor design, so many domains are involved, it is always better to create selections. Like if, there are several selections are made in this way. So this is the stator housing as you are seeing here, so that it will become easier for you to do the whole processing. This is the stator housing. These are the solid materials, solid material parts. Like that, depending on our need, we can create particular aspect. Like this is the air gap boundaries we have here. Like if I check in, yeah, this is the air gap boundaries we have here inside. So all these things can be made accordingly in this manner. Once, and another major aspect here in this is that since in a motor, since the rotor is a moving domain and stator is not moving, that is why we have two options, either to form a union or assembly. In motor, we have to go for an assembly by creating an identity pair, saying that in the middle of the air gap you can see a particular boundary as shown here. So in this is the boundary that acts as the separation between the stator domain and the rotor domain when it comes to simulating. So we are specifying that in terms of an identity pair. Whenever we are dealing with COMSOL, we have to make sure that only one identity pair exists between the stator and rotor. It comes in handy mainly when we are dealing with the CAD import geometries, because in CAD import geometries there can be several domains, but ultimately while fixing the geometry, we should make sure that we only have two specific domain objects. One is the stator and the other one is the rotor. Once geometry is made, then we will assign properties depending on the different aspect. Like the soft iron is applied to this domain, and the copper is are the conductors. This is the conducting magnet we have, and the outer casing is the high alloy steel, as you are seeing here. So this way, we have a material library which we can incorporate in this way. Like here we can see we have an elaborate material library consisting of both built-in and particular physics aspect material models that we can directly use it in our simulation. So this way we have to just drag and drop or double click, and that will get into this model as you are seeing it here, air or whichever be the material we have. Now, once all the materials are assigned, we are ready to apply the physics, and that is where I have already added, as I said, the magnetic field machinery, and again the rotating time periodic aspect. So in this particular, once you add this physics, it will be applied to all this domain. Which means that it is going to solve based on the FEM approach, the whole all over magnetic or electromagnetic field involved in this area. Now here we will be specifying some aspect like what will be the out of plane thickness of or the total length of the rotor. Then what is in terms of time periodicity, how much is going to be the rotational velocity of the rotor, and this is a major aspect. Like out of this time periodicity, we are aware that rotating magnetic field is going to repeat after a particular number of time frame. So how many number of time frames you are going to simulate, that will give have an effect on the accuracy of the overall setup. Like if you are only simulating, let us say only 4 instances, one here, another one here, another one here, and then the other one here, then in terms of the electromagnetic field solved or the magnetic field solution, it might not be that accurate. So when we increase the number of time frames, we are really able to get the time and space varying magnetic field very clearly, and that is why there exists an optimization in terms of the number of time frames we should use. And again, some more other details are there which can be very clearly understood based on the settings are given here. I am not getting much into the details, but major aspect here is that one thing is that we are defining a rotational boundary pair as here as assigned. It will come in we have to assign it here, like between the stator and rotor. As I said, this is the juncture where we are restricting the motion. Like this side will be moving, the other side is not. So we are giving this rotational continuity pair. And another one is the rotational periodicity aspect, because we are exploiting the symmetry. That is why on this side the periodicity aspect is used over this side, as you are seeing there. And in the rotating domain, we are specifying that the rotor is rotating. All this physics, some of them will be already there as default, but specific boundary condition we can always add by right clicking on this one on the magnetic machinery and see the available options. Like you want to add the laminated core part here, that is already added, so that we will be able to specify whether we are using Steinmetz or Barotti condition, or if we want to add magnet, then we can do that. Another very good aspect in COMSOL is that we have an automated multi-phase winding aspect that is already included here. So in the automated multi-phase aspect, we will specify our current and initial angle and the frequency. And here we are choosing an automatic three-phase kind of an arrangement where we are specifying what is the number of poles as well as the slots. And how much number of coils are there per slot. So once it is defined and we click the or add phases, automatically it will give us like the where the R phase or the A phase is going to be, where Y phase is going to be, and where the B phase is going to be. And internally, in what all places we will have the reverse current direction. Like either current will be coming in or going coming yeah, out of this plane or into the plane. So all these things happen in an automated way in COMSOL by applying the multi-phase winding, but also allows us to specify it in a user-defined model. Like you are defining an n-phase motor or a kind of an aspect, then we can do it by ourselves based on design. So this way, we are defining the magnetic machinery. So as you can see in the magnetic machinery part here, we are trying to solve the Maxwell's equations in the time periodic aspect, as you can see here. So that is getting solved. Another aspect will be in solving the heat transfer. In heat transfer, again, the heat transfer in solids is used so that all the solid domains are selected under the heat transfer. And some domains, either there can be thin layers, like when you have the slot and the outer stator core will have a very thin layer of insulation, let us say, or thermal insulating part, which will play a role in the overall heat transfer mechanism. So that is defined here in this case as the thin layer as you are seeing. So the thin layer, in the laminated core. Sorry, this is the thin layer with the laminated core and the housing. Like this is the housing and this is the laminated core between them. Similarly, in the winding insulation also, we can define a thin layer approximation where the thickness of that layer can be specified instead of really making the whole geometry and making the computation complex. Instead, we can go for thin layer approach. Another thing is the cooling offset. Either we can involve CFT here and see the whole scenario, or we can use a simplified version using the heat flux, as you are seeing here. We have different options of heat flux, and in this case, the convective heat flux is chosen on the outer water jacket, or we are assuming that we have an active cooling kind of a mechanism, giving the heat transfer coefficient as a higher value, 500, which we will understand based on design. And similarly, another way of cooling or the heat transfer part happening is in the air gap. So in the air gap case also, we can define a particular heat transfer coefficient depending on the rotation or the flow velocity, as well as the external temperature here will vary, because towards outside we will have the ambient temperature, but inside the stator will play a key role in the overall temperature in the air gap. So that is why we are using the average temperature in this case. Now we have two physics here. One is heat transfer physics. As you can see here, the equation is different. We are using the heat transfer physics to solve it, and in electromagnetics we are using the Maxwell's equation, but both are coupled here through the multiphysics coupling. And in this case, we are using the electromagnetic heating, because this way the losses happening in the stator and rotor, or the every part in this motor, will be coupled with the heat transfer module through this multiphysics coupling. So that is what is done in this case. So our losses will be taken from the electrical domain, and it will be applied to the heat transfer domain. Once it is done, then we go for meshing, as you are seeing here. We have an option to either go for user control mesh or physics control mesh. In a normal scenario, we can go for physics control mesh with the different options available, or we can go with user controlled mesh. And there is an option also for importing the meshes from another interface as well. So this is how we will be setting up the overall motor model in COMSOL. Once the whole setup is done, we can, as I said earlier, how many number of time frames are involved will have an impact on what will be the how accurately our field is getting calculated. So in this particular study, we are trying to evaluate the effect of time frames, and this is called as a parametric sweep. So we are sweeping a particular parameter, in this case the number of time frames, from 10 to 240 in this range. So once we are sweeping the number of time frames or time frames, we will be able to see how accurately it is able to predict the losses or the torque involved in the motor. So with the study and in the overall how it is done, in the study, if you click compute, it will evaluate it using the particular solver settings we have. If you see inside, we can see the solver settings here. And in this case, we are using a segregated solver for the magnetic field and temperature field, ultimately giving the solution in a simultaneous manner. Now, if you come into the magnetic flux density plots, taking that. density plot. So this is the result section. So in result section, we can make different kinds of visualization involving 3D, 2D, 1D or 1D plot groups. So in this case, since it's a 2D simulation, we have some 2D surface plots here. As you can see here, this is the magnetic flux density. In the same plot group, we can add different kinds of plots like surface or streamline or contour or a line. So all these things can be done to give you proper visualizations of what is happening inside the magnetic field. So if you see this particular surface in the expression, this is the magnetic flux density, the normalized normal component of magnetic flux density that we are measuring here. That can be selected by navigating through the available options. Like this is the motor magnetic field. If you want to plot a particular thing, then you can come here and select it. And then if you click plot, you will have the visualization in this manner. So this is for 240, which is giving us a quite properly distinguishable field. But once you go to the 10, then you can see that there is some variation, not that effectively visible here, but we will be able to understand it more properly in this particular plot, where I am plotting different aspects of this motor, like it can be torque, it can be torque or the winding losses and all. So if you see up to around 50 or 50 and all, the losses mainly the green one is the winding loss. This is the stator core loss, the rotor core loss and all, and this depreciating thing is the torque involved. So depending on the number of time frames, you can, for the same setup, you can see there is a variation in the predicted value of the losses. And we can see that around a quite higher value, like after 120 or 150, we are able to see a proper stable value for all those values. So that is the way we will be selecting the number of frames. It will depend on particular design. But once we conduct this parametric sweep on this one, we will be able to understand how the effect is going to play a role. And using the 1D plot group, all these things are possible, like how to plot a different aspect. In this table graph 1, as you can see, I'm only plotting the torque in this case. And in the table graph 2, I am plotting different kinds of losses, and two y-axes are involved. This side is electromagnetic loss, the other one is the torque. In electromagnetic loss, different aspect, like what is happening in the winding, in the stator core and the rotor core, or all are available in terms of the derived values or in terms of the evaluation parameters. If you see this particular evaluation group, that is what I am doing. We have a particular parameter which can be selected, as I already mentioned, which is the torque, which is calculating using the RQO torque calculation method. And we can also evaluate the electromagnetic loss density and using the surface integration approach. Like if you click here and right click here, I can go for the averaging or integration maximum or minimum, all kind of mathematical operation to get the quantities I want. Once I know the density, which is the Q dot QH is the electromagnetic loss density. Once it is getting integrated over the whole surface, and we are considering the overall length and symmetry aspect, we are getting the losses involved in the overall motor. This is correspond to the stator core losses. Similarly, this is the stator iron losses, and this one is the rotor magnetic losses. Similarly, we can find all the losses using in this way using the evaluation steps. So this way we understood the time frame involved. Second part will be to understand the efficiency map study, or how with respect to temperature it is going to vary. For that, we are again creating another parametric sweep where I am changing the two parameters here. As you have already seen the simulation, I am changing the rotational speed of the machine as well as the excitation current. Both will have an impact on temperature as well as losses. So these are varied from in this variation. We can have many number of steps on that, but here for a demo, we are only using 3 of them in both of the cases. So once with this parametric sweep, it is calculated. In the stationary mode, in the time periodic magnet field analysis, you can see the evaluation group 2 here as implicated here. Like you need to get the data in terms of a table, like with respect to the rotation and current, how the efficiency, the torque speed, or the losses are going to vary. We are having it in this way in the evaluation group 2, and at the same time we can plot it in the different visualization strategies as well. Like as you can see here, this is the efficiency map that I showed you earlier in the presentation. The same thing getting calculated here as well. In the evaluation group 2, during this evaluation steps, we were calculating either the torque or the shaft power and all. But in this case, in this evaluation group 2, I can also define an expression here, which we here in this case will evaluate what is the overall efficiency. All this integration corresponding losses. Okay. So this way we can see the effect in the similar manner. Now, yeah. So, and as I said, for whatever we in the presentation we showed, the same thing is exactly taken out from the simulation. So this way visualization can be done. Similarly, if we want to see what is the change happening with a particular parameter, we can also use the animation option available here. So this is how we we do the simulation in COMSOL. As you can see explicitly, one thing I would like to mention is that whether it is magnetic machinery or the heat transfer module, or let us say now we are going to add the mechanics module, all are added in one particular GUI, one after other, all getting simulated all getting simulated in a simultaneous manner using our solver. So this is what is happening. I think I was a bit fast, but in the time available, I hope you understood how the workflow works in COMSOL Multiphysics. So we will get back to our, our presentation. Yeah, I hope it is visible. No.
Yes, sir. Visible.
Oh, no. Sorry, no, I think it is not. Is it visible?
No, not anymore.
Yeah, now it is visible, right?
Yes, now it's visible.
Okay. So apart from the motor model, as already mentioned, we can deal with the power electronic modules also in the similar manner, like whether it is electromagnetic field and electric circuits alone, or with coupling with heat transfer and solid mechanics and acoustics in the similar manner, when it is involves cooling. Mainly and like if you are simulating a PCB warpage and all, we can have EM coupling along with the mechanical and thermal expansion and heat transfer to understand the overall aspect in the power module as well. Now this way we can involve power modules. Now a success story of using this in industry is with the ABB semiconductors, where they were trying to understand what is how the hotspot is going to vary depending on the design of this particular current path. And ultimately, rather than the structural design, they came up with an understanding that the current density plays a major role in the overall development of the hotspot, getting into better designs and ultimately into efficient models in this manner. And another way, the same power electronics sector in power sector in inverters, the Bosch is utilizing COMSOL to understand or model the ESR, or the frequency dependence variation of the DC link capacitance. That is one thing with the EM part, but another way they are also trying to understand what is the hotspot temperature development inside the DC link capacitors or the overall design, and how to mitigate it using design variation and optimization. So this way, industries using COMSOL in various aspects in the EM drive as aspect. Now, the new module available in COMSOL is the battery design module, where we can deal either with it in the micro level or in the chemistry aspect using the different kind of models available, or it can be using the different kind of models like heterogeneous models or homogeneous models or like the LEM models. All those aspects are possible, and it is having the major impact is on time, or like how faster you want and how much accurately you want the results. So we can either go for any of this approach, and we can also go from very smaller parts like in the chemistry aspect to let us say the jelly aspect or the complete one cell model, and into the thermal management of the overall battery pack as well. So mainly the thermal management of battery pack industry is using it to a larger extent, like how battery module can be coupled with heat transfer and CFT to understand how the thermal management of batteries in a quite better manner. Now, as I said already, the electric motor drive involves both the motor, then the power electronic converter, as well as the battery. So all this thing together as can be done in COMSOL Multiphysics in a single GUI. That is a major aspect we have with COMSOL. And this is a particular example available in the application library, which is dealing with that. So even though it is not involving the battery module as such, but the power source is given, and we have an inverter circuitry which is getting connected to the synchronous electric motor drive, with a particular design, and based on the PWM pulses, or how you are varying the power electronic converter, the effect can be will be reflected in FEM, which is done which you will be able to see in the synchronous electric motor drive example available in the our application library. And similar to that, if at all you are interested to learn more and to get a hold on the various concept as well as how it is getting modeled in COMSOL, you can look into the motor tutorial series available in application library, as well as several other blogs and blogs as well available in the COMSOL website. So that is the way we deal with a different electric motor. As you can see here, it involves both the electromagnets as well as the heat transfer in this case. With this in this way, and this animated figure, as I said, mentioned, it is not created anywhere else. It is directly taken from COMSOL GUI and presented it here. So that is about the electric motor drive part. And yeah, I would like to conclude it here. Like as you are seeing in the power module, whether it is electromagnetics or heat transfer or a PCB warp page or any other scenario, different physics, it is getting solved in COMSOL based on the fundamentals of physics. Like magnetics is rooted on Maxwell's equations. Those fundamentals we are solving similar to any other physics, and we are able to solve it in a multiphysics approach in a simultaneous manner without any restriction over how many number of physics you can add, giving it a way, making it very useful when it comes to realistic design and optimization of the electric motor drives. So now I think I will take questions, and I hope you can answer this poll question, like after going through the webinar, how you would like to connect with us.
So, thank you so much, Dr. Nelson. Our audience is filling in the poll questions.
Yeah.
And in the meantime, I'll just go through all the and list all the questions for you here.
Okay, in Q&A, right?
Yes, for the Q&A. Before that, I would like to once again thank you for that informative and engaging presentation. I'm sure our audience gained some truly valuable insights into the evolving landscape of electric motor and drivetrain design. So I'm ending the polls now, and we'll be screening some of the questions that have been posted by our audience here today.
Yeah.
And one of the first questions that we have received is, how do you model transient or peak load conditions, higher current density regions in your drivetrain simulations to account for real world current draw battery?
Yeah, I hope he's talking about the transient conditions. Like as I said, let us say if it is about a starting condition, or in between, or the normal operation of a motor, you have a short circuit fault or kind of an thing. Then there are two approaches. Either we can make the variation in the excitation given in as an analytical waveform, analytical function, and give it the, or if you have a particular circuit scenario where you are starting a motor, you have a inverter with a source, and how the real world scenario that can be modeled using electric circuit and coupled. Both ways we can account for this, but ultimately it should be done in the transient scenario, because you are trying to see what is the effect during starting or under a fault, I think. So anyhow, it is capable, that capability is with COMSOL. There are some examples as well. You can connect back. We will be sharing with you.
Thank you. Next question is, are non-linear magnetic materials supported?
Yeah, as I mentioned already, nonlinear magnetic materials are supported. We have an extensive material library where some of the nonlinear behavior is already accounted for. But now let us say you have an experiment, you have conducted an experiment on a material, and you have particular material property variations as well. So in that aspect, you can you can utilize that data and give it in, let us say, in the material property section, and model it as well.
Okay, thank you. Next question is, can I import my own motor geometrics?
Yes, that is very much possible. As I said, mentioned in the showed it in the while geometry, there is an import option available in COMSOL where the standard geometry files, like maybe you are working in some other standard CAD geometry softwares, you can directly import that geometry from there, like a step file or a DXF file or a DWG file. All those formats are allowed in COMSOL. We can import it. Then even we can work on the geometry as well. Once you import the geometry, we can work on that as well. So that is possible. And you can import meshes as well. In some softwares, you will be having mesh as it is. So you can import mesh and work on that. That possibility is also there.
Next question is, how are you balancing the torque on flat and sloped surfaces?
And I think that needs a bit of an understanding. I'm not really getting what he meant by that. In terms of torque calculation, we are depending on the RQ torque calculation method, where you can say, he's writing something. Yeah, is the air gap plays a vital role. I think that is from him again, if I am not wrong. So yeah, air gap plays a vital role, but in RQ torque calculation method is quite good in that manner. But what you have to take care is that at least, let us say, 3 or 4 mesh elements should be there, because it depends on the number of mesh elements available in air gap as well. So we normally keep like a 2 or 3 number of mesh elements on both sides of the air gap, towards the stator side as well as the rotor side. So you will have the proper result. Again, by going through 1 or 2 parametric steps on the mesh elements on that area, you will come to know whether you have an accurate result or not. I think that answers the part.
Next is, how can you model the impact of varying load conditions on the performance of an electric motor and drivetrain system?
Okay, yeah. Again, by meaning like the varying load conditions, we can do it 2 ways. Either by changing the excitation part. Another one is like, if you really want to learn the transient behavior of load, then we can have magnetomechanics involved. And in magnetomechanics with the solid mechanics, we have this magnetic rigid body condition. With that, we will be able to understand with respect to the load variation, we can clearly understand what is going to be the performance of the motor. That is the easier approach with that. Now, if you are looking for deformation, that is another aspect. But varying load condition, this can be done. Another way is that implying the same thing using the electric circuit or the excitation condition. Both will give you the sufficient results.
Okay.
And I think another question is coming from the same person. What optimization techniques are available in COMSOL for enhancing the performance of electric motor drivetrains? Okay, yeah, as I said, there are like parameter, shape, and topology optimization. I explained it already. So depending on your optimization perspective, like what you want to optimize, the particular methodology will change.
Next question is, can I include a fluid flow model for motor cooling?
Yes, you can. Yes, you can do that. As I said, in COMSOL, there is one advantage we have. We don't have any restriction on which physics we can include and which we cannot. In some of the physics approaches, we already have directly available multiphysics coupling. If at all it is not available, still you can couple particular, like you have a particular force on magnetic field, magnetic force on one domain, and there is not a particular coupling is not available in solid mechanics to couple it, but still you can use that force and give it as a boundary load or a domain load in the solid mechanics part. So there is no problem with that. Similarly, in motor cooling, already like in heat transfer and with the CFT, we have a direct coupling. So that way we can couple the motor cooling aspect as well. In this particular scenario I explained, it was only like an approximate manner through heat flux, but we always have that option to put in active cooling by specifying the inlet and outlet and how much is the flow velocity and all.
Okay, we have a lot more questions, but I think we can take 1 or 2 more, sir, if that's fine with you.
Yeah, I will just.
One last question.
Yeah, 1 second.
Okay.
Okay. Yeah, one question is like, is external scripting like Iron Python is supported? So Python is quite different from COMSOL, or we don't have any direct links with Python. Like if at all you are working with MATLAB and COMSOL having a direct interface as such. But once you are done something in COMSOL, you have your results, and then you can manually take it to any other platform. And but as of now, there are no like direct couplings with Python as such, so that we can have a cost simulation kind of an approach. I hope that answers this query.
Yeah. Thank you so much, sir. And heartfelt thank you to our audience as well for their active participation.
Yeah.
As we draw this session to a close, we'd like to extend our deepest appreciation to COMSOL for their unwavering support and to all of you for making time to join us today. We look forward to welcoming you again soon for another engaging and knowledge rich session. The floor is now open for networking, and we also have a dedicated breakout room available. And I encourage all attendees to join in and take this opportunity to connect with Dr. Nelson directly for any further discussions or questions. So, thank you all once again for your participation, and we wish you a wonderful day ahead.
Thank you so much. Thank you so much for your time. May I know how to get into the room?
Yes, sir. In the more
I
sections,
got it.
we
I
see the breakout room. Yeah.
got it.